Testing. So, mining software development history, which is a topic not really popular one, not everybody knows. This is actually a separate domain of machine learning. Oh yes, it works. Yes. The plan of my presentation today will be something like this. First, I'll give you a quick introduction to the topic, explaining what is machine learning on source code, try to highlight the most important and widespread topics in this area. Then I'll give you 3 examples. The names don't matter that much, so you can just bypass it. And finally, end my presentation with a brief overview of the tooling and the data sets which you can use if you want to practice it yourself. So, the introduction part. How many of you are software engineers? Don't be shy. So, those are software engineers. You should know about version control systems, and most likely you are dealing with Git, right? Others are not so widespread in 2019. So the good thing about Git is that it's pretty much well structured, right? Just a quick overview of how Git works. This is important. Git stores your changes in commits, and the commits can have multiple parents, and commits can have multiple children, and they form a directed acyclic graph. Then each commit can have some metadata, such as an author, or a committer, or the date it was created. And each commit is actually a snapshot of your project, like an abstract one, not in a real file system, but it can emulate it. And you can compare these snapshots. You compare each consecutive comment to the previous one and see what has changed. And this gives you the so-called difference. What has changed in your ready. And all these entities, they form a graph which you can study one way or another. If you look inside the changes, if you look inside the source code which is stored in Git version control system, you'll see that it's also a graph. Because if you want to execute source code, if you want to do something useful with it, you're going to parse it, and the artifact of this parsing will be an abstract syntax tree. If it's a Python, you don't compile it, right? You interpret it, or anyway you have to parse it. If it's like C or C++, you compile it, and parsing is the first stage of your compilation. So you have a graph inside of a graph, right? Because Git is a graph with all these entities in the previous slide, and the source code is also a graph which is inside. Everything is a graph, and this is actually good news because graphs are very well studied in computer science. You can apply many different algorithms and other swagger to do something useful. And also, machine learning is also studies graphs. You can start with quite straightforward and obvious things like measuring something on a graph, centrality measures, or measuring page run. So I guess everybody uses Google in this auditorium, and as you recall, Google started from the PageRank algorithm in 98 or 97, if I'm not mistaken. The algorithm itself is quite obvious. We just formulate it as a matrix, and then we do power matrix multiplication and get a number for each node in your graph. And this node corresponds to an importance of each node in your graph. If your node connects to many other nodes, and these nodes are kind of important, then your node is important too. And if your node is on the outskirts, not connected to many other nodes, or connected to not so important nodes, it gets a lower number. So this importance estimation was used back then for ranking the web pages you can use the same here. And there is actually a startup named sourced.tech in Silicon Valley. The founder of the startup is a former TensorFlow developer, by the way. The idea of the startup is actually pretty cool. So you look at the changes exactly as I explained as a graph, run PageRank on the issues were created by developers, and so on the source code, on the changes, and you estimate the importance of each developer in the software project. And then you can have a budget of bitcoins or any other cryptocurrency, sorry, and then you spread your crypto coins across developers relative to their impact, to their importance determined by PageRank, automatically. So you don't have to do anything. And it's a very nice idea, especially for open source projects. You can try to apply some ML algorithms like node embeddings. I'm not sure if you heard about node2ec. We'll speak about embeddings a bit later, so if you haven't, it's not a big problem. So node2ec is like a de facto standard of embedding nodes in your graph and turning them into useful dense vectors which you can compare to each other. You can apply community detection, you can cluster nodes. This is also like tens or maybe hundreds of different models in machine learning for clustering and for community detection. It's pretty much well studied. Or you can go with deep learning and try to apply something sophisticated. One example is a gated graph neural network, where you have messages coming from one node to another in your graph, and then you apply gradient descent, either in PyTorch or TensorFlow, it doesn't matter. And it is proven in papers that gated graph neural networks can emulate and solve pretty much every computer science problem in a graph. If you say the shortest path problem, so if I say shortest path, do you remember which is like the most widespread algorithm for finding a shortest path in a graph? Yeah, so GGNNs can emulate Dijkstra and work exactly like it and solve the problem. So they are pretty universal in this study. So finishing the introduction with diffs, it turns out that although you can formulate pretty much every problem as a graph problem, it's not always a good thing to do. And diffs is one example of that. If you run git diff, for example, to find the changes in your commit, you'll see that there are some removed lines, some added lines, and that's it. So Git doesn't try to parse your source code to do something useful. And there is a reason for that, because if you want to compare previous file and the new file, just line by line, there is a very efficient algorithm for that called Myers algorithm, which works in linear time from the size of the changes and also from the size of the file. So it's quite efficient. And this is why everybody uses it, because it works fast. If you try to do the same, but looking at the source code as a graph, you'll get into trouble. Of course, if you, let's say, constrain yourself to just only two operations, removals and additions, you'll still end up with a polynomial algorithm. That's fine, but you don't really want it. You want also to add the third type of operation, which is move a node from one place to another. Otherwise, I can generate a pretty obvious edit script for turning a graph to another one just by removing all the nodes and then adding the new graph. Nobody wants this difference, but just by using two operations, this is often the case which you end up with. And this move operation, it ruins everything. It turns your problem into an NP-hard problem. There are no efficient algorithms for that, and it's a topic of very active research in academia. It's not really solved. So this is why when you run git diff, nobody tries to parse source code. Although in theory, you could. In all the existing mining applications which I have have heard of or I'm using myself, you use a hybrid approach where you still compare lines by lines, but also annotate them with AST, so you understand that a specific line corresponds to a specific unit in code, like class or function or variable. So these objects form the machine learning on source code domain, where you try to apply machine learning to well-known or not so well-known problems in software engineering to improve the way you develop source code, to improve how you write it, one way or another. And the first example which I want to demonstrate is couples. So what is couples? The idea is quite simple. If you look at the comments which contain the same file in the changes list, you can suggest that these comments have something in common. And if some file gets changed by several commits written by different authors, then you can suggest that these authors also have something in common. I mean, if you change the same file, probably you know how it works. And you can try to find a group of people who change more or less the same source code, and you can say that these people have something in common. They have more or less similar experience, or they know the same topics, so maybe they are from the same team. You can use it. And you can kind of invert it and look at it as commit to file, and you say that if a group of files often appear together in a commit, then also these files have something in common. They are coupled. The most obvious example of that is when you have tests. You change your API. You also quite often change the test because your class names change it, or your function names change it, or your behavior changes. So you have to maintain your tests here, right? And when you change files together, they are coupled. So tests and the actual source code which solves the problem. There are other examples of this coupling. If you do a large-scale refactoring, I don't know, if you rename a method which is used in many different places in your program, you also have to change all the files which are using them. And these files get coupled. And if they often appear together in the same commit, they're definitely coupled. They have something in common. And let's try to visualize it, to show it, to reveal it using machine learning. So, word2vec, we are going to use it. Well, not the vanilla one, but just the idea from behind. I'm not sure if you heard about word2vec. I'll give you a quick recap of what it is. So word2vec is an embedding algorithm which tries to turn every word in natural language to a dense vector. Well, you can do it in many different ways, right? Whatever. But the germ of the method is that these dense vectors have one important property. If you measure the Euclidean distance or cosine distance between a pair of vectors, it will be small for words which often appear together, and it will be big if these words have nothing in common, if they never appear in the same context. And also, they allow you to do algebra operations. This is like the classic example of word2vec query. When you have king and queen, and also man and woman, you take vectors, you subtract from king man, you add a vector for woman, and you get a vector which is very, very close to queen, which is quite nice. The model tries to understand the relations in the natural language. So, if you read the papers, you find out that word2vec is actually trying to optimize the so-called point-wise mutual information. This is a metric for capturing the similarity If you have items which often appear together, your point of future information will be big. And if you have redundant, irrelevant items, your PMI will be very low. And you can calculate this PMI optimization problem. You can solve it in different ways. You can apply gradient descent and just read your data set batch by batch. And this is what the original paper did. But also you can first build the explicit matrix with the concurrence and then try to embed it. So just being a bit more specific, imagine that you have a square matrix. Every row and every column of this matrix is a word in a natural language, right? And the value of the cell on the intersection of a pair of words is just how many times this pair of words appear together in the same sentence. Then you apply some black box, some magic, machine learning, you embed it, and you get the results. You get this algebra and so on and so forth. So let's try to optimize the PMI, but in our case. In our case, we still have a notion of a context, right? If files appear together in the same commit, we increment the corresponding cell in the matrix by 1, or if a pair of people committed to the same file, again, you increment the value in the matrix by 1. You build these matrices, and you apply all the well-researched methods from embedding, word-to-vec, swivel in particular in our case. And you get the embedding, and you get these nice properties, and you can do algebra on top of files, or on top of authors, and it works quite nice. However, there are some problems. I'm not sure if I should really go into much detail about the problems. So, as usual, there is no silver bullet, and there are always some limitations of every method. And embedding on an explicit matrix also has some limitations. So if you try to do this, ping me, ask me, or just read these lines, and it will be more clear for you. So once you get the embeddings for every author or for every file, you would want to visualize it, to just understand that everything is working fine, because otherwise it's just a bunch of vectors and you don't know what to do with it. I mean, it's completely obscure. So the classic way of visualizing word-to-vec-like embeddings, they don't really have to be word-to-vec, they're used quite often with word-to-vec, is TSNE. So TSNE can be looked at as another type of embedding, but just only for 2 or 3 dimensions. It works best for 2 or 3 dimensions. So the word-to-vec-like embedding is 50 or maybe 300 elements. So you have the space of dimensionality from 50 to 300, which is huge. You want to turn it into just 2 dimensions and then visualize it. I mean, the paper, the screen is 2-dimensional. You would want to have 2-dimensional embedding. So you run it once again, and this is an example of what can be seen. The algorithm is run on top of the Linux kernel, and you see the nice grouping of files in the Linux kernel. You can do the same with these authors, and also you get the same insights that some people are placing together in 2 dimensions or 3 dimensions if they have something in common and they share the knowledge in the project, exactly as we would expect. And this ends the first example. The second is what we can do with lines, with diffs, and things like that. So this is an example of a burn down, how to calculate the burn down. Imagine that you have a file. The source code is in Go. I don't really care if it's Go or Python. It's not really the case. So in 2014, the file was created, and it was 3 lines. And for simplicity, in 2015, you have a first change in your file, and you add another function. And you record how many lines are still not overwritten and which were created in 2014, right? So 3 lines were created here, and still 3 lines are not overwritten by 2015. In 2016, you add more changes to your source code. You change the second line here. You add some declaration of the constants, and also you rename the function. So now you calculate how many lines which you added in 2014 and not overwritten in 2016, and the answer is 2. How many lines which were created in 2015 are not overwritten? The answer is again 2. And how many lines were created in 2016 and not overwritten in 2016? Obviously it's 3 because it's the same year. You can plot it nicely, and you'll get this diagram, which is called line burndown. It just visualizes what I just explained. So you have 3 lines here. They are constant until 2015, and something happens, and you have 2. The same with the red band. You have some linear approximation here. We expect that these 3 lines were uniformly written during the year. Of course, it's not the case, but you don't know the more detailed statistics. And finally, you have some 3 lines here. So this is a 2 example, and this is what you get if you analyze a Linux kernel with this method. You'll see that initially in 2006, when the Linux kernel was placed under Git, you had roughly 750,000 lines of code. And then this number gradually decreases because new code is written and also the old code is being changed. And here finally you get roughly 2 times less than you used to have in the beginning. And every year Linux kernel has more and more source code, and you have more and more bands. Some years were more productive, some years were not so productive, and it continues to grow until 2019. It will continue to grow after 2019. So the picture is nice, but the question is, where is machine learning? So where is the math? Where is the hardcore algorithms you want? And Eric Bernardson, which is a great software engineer and machine learning engineer who created Luigi, for example, or Unknown for 10 Years Neighbors. He wrote a blog post in 2016 in December just about burndown. I think he was the first who suggested this idea. He went a little bit further, and he applied Kaplan-Meier to visualize the cohort analysis, how the lines of code are expected to change through time. So you'll see that there is only 1 line here for each software project. The list of software projects is somewhere there, it's not visible. Anyway, you have just a single line for every software project. And remember, on the previous plots you had several bands. So how do you switch from several bands to just a single line, which is an estimation how many lines will be still alive through time? You don't have the data, right? Because for the first period, you have the full history. For the second period, you don't have the data for the first year. Somewhere here, you just know how these lines will change it through time to the right, but not to the left. So every time, you have a little bit less information about a specific cohort. So Kaplan-Meier is a very classic, let's say, way to address this problem, and you can just use a black box, apply it from Python or another language, and draw this line. So how to read this plot? The plot is 100 initially, always. This means when you create source code, initially it's not overwritten. And then through time, the number of lines declines until 20% in 2 years for the project. And if you ask me what this project is, the answer will be Angular. Angular gets rewritten every few years. This is like a great example of applying ML or stats analysis to software development observability. How do you, let's say, use it in your daily life, right? I mean, this is cool. This is cool to plot this, but what's next? Turns out that this is a good indicator of your architecture. If you overwrite half of your project every few months, then something is wrong. Probably you should just sit and think hard about the whole thing. Maybe you're doing it wrong. You should not overwrite half of your project every few months. This is not normal. So you can also track the ownership of every line. Instead of just tracking the year, you can also add the author information. And you can calculate exactly the same stats, but for different authors. This plot is for Ember.js, if I'm not mistaken. And you see that shortly after 2014, you get 2 new contributors to Ember.js, which is a front-end framework, if you haven't heard about it. And these 2 core contributors captured half of the project, even more than half of the project. And the guy here actually took more than one half, as it seems. So these 2 people actually control the whole thing. If you say that you don't want to build a feature, the rest of the folks will not have the majority, and the feature will not be implemented. This is how it works in open source. It's also democratic after all. And I consulted with another core contributor, which is somewhere here, who used to work in our company, and I asked him, what did he think about it? And he confirmed that indeed there is a problem with that, and there is actually a joke website about Ember.js where you just go to the website. It's quite minimalistic. There's just black text on the white background, and the question is, how many people know Ember.js internals? You open it, and the answer will be like 2 or 3 people. This is a joke about Ember.js development programs. However, you should not really trust this graph, this plot, because estimating the ownership in a project is not as simple as that. It's not enough to blame line by line and plot this and hope that this will be the answer. The reality is more complex, because imagine that you wrote 100 files in your project. It could be a deep learning for image recognition, and you wrote 100 experiments in Python. You just wanted to explore all possible hyperparameters or possible use cases, or possible preprocessing for images. You did a lot of work, but in the end, in production, it will be only 1 file, not 100. And in this one Python file, you'll use the best hyperparameters and the best preprocessing which you've discovered in your experiments. So you see what I mean? You spent a lot of efforts, but the actual plot like that will show you as something here. I mean, you will not get so much credit. And this is a problem. So you need to take into account not only how many lines are not overwritten and they are still yours, but also how much efforts you put before, how much source code you contributed in the history. And also, you should probably apply some weight decay, so it's your time. You don't care about efforts which you did 3 years ago. The project was quite different, and much things have changed. Now, people don't care what you did 3 years ago. You need to understand the current API, which you currently don't have experience with. So you have to do many things, and the final metric which you build will still be quite inaccurate, fortunately. So, yeah, this is quite complex area of research in engineering observability. However, Again, we are speaking about machine learning, so let's do something with ML. And we'll do something with ML by using this type of plot, which is called overrides. How is it structured? You have an author at every column and every row, and the color intensity or brightness corresponds to how many times your lines were overwritten by your counterparty. So imagine that you write 100 lines, so Anders wrote 100 lines, and 50 were overwritten by himself. That happens. And then I have 10 were written by other contributors to the project. So you end up with this matrix with numbers, right? We already know what to do with this matrix. We did it in the previous example. Let's try to embed it and plot it. And indeed, it's possible. And you get the same nice grouping in the space. You would expect that if people often overwrite each other and form clusters, then again, they have something in common. They share some common knowledge. Or maybe, like in Wikipedia, they are fighting with each other. You know, the war of edits. So we can do the same in source code if you're managed by a bad team leader. So you see that, I don't remember what is the project in this example. I think it's Git, maybe, or maybe it's in Node.js. So you will see that all 4 contributors are indeed grouped to the same cluster. So this works nice. Ending the example with lines importance, which is an area of active research in our company, and I know that other researchers are actually exploring it. The goal is to map every line in your program to some number which would indicate its importance or its hardcoreness. In this example, you will see that it's in Python. I hope most of you know Python. If you do some, let's say, well-known import, it's not considered as important because imports is something everybody knows. However, if you import some not so well-known Python package, this is getting more interesting. And then you define a function. Well, the function itself doesn't really matter much. You will look once at the declaration and that's it. Then you do some logging. Logging is not important. You can live without logging. Then there is a comment. Well, comments would be nice to have, but if you remove all the comments, the program will still go the same way. And the next line is probably the most important in the whole snippet. You'll see some shady condition with some parameters, and also you do some comparison with a magic number. The number is very shady, and if it's changed, then it's definitely worth your attention, definitely worth considering it during the code review, for example. Then you return another magic number. It's still important, but not as much because not so much logic in just returning a number. And you also do return 0, but return 0 is quite widespread. You don't care about return zeros. So you could try to build some machine learning model to estimate the importance of every line and then use it for code reviews or for calculating how much hardcore or important source code each developer in your project has written. Plot it and find some insights from that. Well, we haven't done it yet, but as I said, we're actively exploring the possibility. Okay, and the third example related to time series, which is also quite funny. Let me start with an example. So, Python contributors. There are many implementations of Python. One of them is CPython, the default one. It's written in C. Started in '92 by Vadim Markovtsev. It's not included here for clarity. So this is just the list of 8 core contributors to CPython, which I took from GitHub. Everybody here took at least 500 comments, if I'm not mistaken, so they are really, really core people. And you will see that, surprisingly, some of them disappear after some time. And actually, all of them disappear after some time, except the ones which joined pretty recently. For example, Fred Drake joined the project in '96 and abandoned it in 2004. We don't know what happened to him. Maybe he lost his interest, maybe something else. But the fact is this: he is not contributing to Python anymore. And the same people like this guy, they also stopped at some day. So let's try to find some insight from that. Let's try to analyze it with machine learning, with our embeddings, and other models which we have studied, and reveal the truth, reveal the hidden knowledge behind this data. So what if we had a way to rearrange people like this? Well, I'm pretty sure that it's not so clear yet, so I'll just highlight this as a full height rectangle. You will see that people are grouped so that the similar, let's say, intervals of activity, they are under each other. You will see that 2 guys stopped in 2012 and they both started in 2000, and another 2 guys ended in 2018 or somewhere there, and we have 2 new core maintainers which joined in 2012 and they are still active. So let's do this at full scale. CPython has more than 1,000 contributors. How about visualizing the flow of the project? How many contributors joined at some time? Let's try to group them and also see how many of them abandoned the project. Probably we will find some loss and some data correction, right? If you see that all our contributors tend to spend not more than 2 years in the project, then we're doing something wrong. Maybe we should pay more attention to how we govern the project, or how we deal with people, how we manage them. This is how we are going to do that. First, we'll define the distance between commit time series. So imagine that we record how many times you committed to the project on a daily basis. So at day 0 you created 3 commits, at day 2 or 3 you created another commit, and then at day 60 you created another commit. So you record this time series. Time series are pretty straightforward. And we define a distance between each time series and another time series. Given this distance, we will try to order by the distance to cluster and run some similar algorithm in 1 dimensions to get linear list, and also in 2 or 3 dimensions to get this nice tensor board-like image of people grouped together by this property. And finally, we will also be able to run queries and find nearest neighbors. So we will ask which people are similar to a specific one in our software project who have roughly the same commit activity. Maybe they are in the same team, or they joined at the same date and they are similar in an open source project. We will be able to answer that. So let's define the distance. Okay, let's do that. And gradient distance unfortunately doesn't work. You just take this series and you subtract from one vector another vector, you find the square root from the sum, and you realize that in both cases the distance will be the same, just because we are calculating. So you have to think a bit harder and find a better metric. And there is one which is called dynamic time warping. Technically speaking, it's not really a distance measure, because it doesn't satisfy the triangle inequality, but for our use case, it gets very close to that, so we can use it. It's empirically proven. The idea of dynamic time warping is to map from every element in one times of the first time series to the corresponding element of the second time series. And then you do it in a way so that the sum of distances is minimal. So you solve an optimization problem. You can look at it as a linear programming problem, and the complexity will be quite bad. It will be cubic or quadratic, since it's quadratic. Yeah. You can apply another algorithm, which is called fast dynamic time warping. It works in linear time. It gives an approximation. It doesn't solve the exact problem, but it's for our needs. So yes, let's use it. For those of you who deal with Python, there is a Python package. You can just apply it and calculate the distance between two time series. And if you want to compare everybody to everybody, obviously you have worse complexity, you multiply by the number of elements. So overall, after applying, let's say, this fast approximation and going smart, you still get with a quadratic complexity of calculating the distance matrix. So is it bad? Yes, it is. Quadratic complexity really bites you, but you can do it only once and try to cache things. So for small and medium scale projects, it's not a problem. For projects like TensorFlow with thousands of contributors, it gets a bit more difficult. Anyway, imagine that you have this distance matrix, almost distance matrix, because as I said, triangle inequality unfortunately doesn't hold. Let's rearrange it and review the ordering. And the most straightforward way people use for ordering this type of matrix, in other words, a heat map, is apply agglomerative clustering, for example, from Seaboard. I'm not sure how many of you did the data science before, but like if you open the data science tutorial, on the first pages you will see these words. You will see that just apply this function to any heat map and you get the result. This is like 101. It doesn't work so well, unfortunately. So let's go smarter with it. So this image is actually a photo of a man, but it has a twist. Every row has pixels randomly shuffled. And it's a square matrix, so every column also has the pixels randomly shuffled. However, you have the guarantee that all pixels stay in the same row or in the same column. So how about trying to reconstruct the original photo from these random nodes? Is it possible? Turns out that yes. If you apply agglomerative clustering, you'll get something like this. You will see some fine structure, you try to find some clusters, but it doesn't give you the result you want. You can apply another technique which is called seriate or seriation and actually reconstruct the original photo byte to byte, which is amazing. This idea was first suggested by Nicholas Krachton in his blog post a few years ago. And let's use it. Let's apply seriation to our dynamic time warping based distance matrix and reveal the hidden structure in commit time series. This is how it works. You define the problem again as an optimization problem where you have to minimize the sum of distances between each element. You define the distance, you have the distance matrix, right? So you have the cost from transitioning from one element to another by definition. So let's find a path which covers all the elements, all the items, so that the sum of the distances will be minimal. And I'm pretty much sure that you have heard about trailing salesman problem. It's a classic computer science problem, and it's defined exactly like that. You have a set of points. You have the matrix of distances between each point and each other point. All of the distances will be infinitely high with reasonable low, of course. And you need to find the root so that the sum of the edges is minimal. It's exactly the same. So you apply the well-known, the well-studied algorithm for TSP. Well, it's not hard, could be of course better, but there are good heuristics and they work with all reasonably big sizes of the problems. So we apply it to our commit time series and get the results. This is how it looks like for TensorFlow. You have the bot, which synchronizes with Google internal copy at the top. You have a few core contributors here, and you have a few guys which have abandoned the project, they no longer contribute. And then you get this ladder. You have more and more new people who join the project and continue contributing to it. Some of them lose their interest and they are nicely grouped in one dimension. It's nice, but it could be even nicer. We could cluster people in one dimension and find groups of similar developers. We can do this by HDBSCOM, which is a novel clustering algorithm which requires 0 parameters from your side. So literally just call a function without any parameters and it works. Of course you can tune it if you want, but you don't have to specify things like the number of clusters or the distance between each pair of points where they should be merged or something like that. So it's a no-brainer, which is why I like it. So you apply it and you will see that indeed people are nicely grouped for the way they contribute to an open source project. Some of them abandoned, they are grouped, and the bot is considered an outlier. So it works without any supervision from a human. Completely unsupervised. This is cool. And the next point in our plan was to plot it in 2 dimensions. It's again possible with models and algorithms which I already explained. It's TSNE. You can also apply UMAP, which is kind of TSNE but works better in some cases. You apply it, it works. Unfortunately, they all leverage the triangle inequality, so it's not so good from the mathematical point of view. I mean, they have some spatial trees which are grounded by the triangle inequality, and our matrix is not so good for them. But in practice, it works surprisingly well. It still works, although from the methods, it's a revolution. All right. So how much time do I have? Perfect. So finishing the presentation with the available tooling, in case I raise your interest and you would want to play with ML code and mining, software history, and software development, artifacts. So which tools would you use? You'll quickly realize that the best way to deal with this is to work with the original data in the original format. If you're analyzing Git repositories, you would not really want to convert them to a SQL database or do some transformations. You would like to work with them as is, just because they get updated, and this means you have to synchronize it with your internal representation, and it's a lot of work which you don't have to do. And this is a concept of code lake, similar to data lake, which states exactly that. We want to analyze our data, potentially big data, in the original format. This is a tool which works as we want, Git-based. Surprise, it's from sourced. There are other tools not from sourced, but I'm from sourced, so this is why Git-based is presented. So Git-based allows you to write a SQL query on top of your Git repositories and why not, to find anything. It has all the insights inside the Git history, which you can query, right? So here we ask for the commit author name and just the head revision, so the latest revision for every repository, and you get the answer in a matter of 3 seconds, which is awesome. You can also augment it with a parsing solution, because remember the introduction, source code is a graph, parsing is a graph, so let's use it. Let's query the graph in the source code. Let's parse it and find something useful. So Babelfish is an example of code parsing at scale, where you have the unified interface for different languages. I mean, every programming language has a different type of AST. Go has one AST, C++ has another, and Python has a third one. And all the entities are named differently. Well, some languages have classes, some languages have structs, some languages have exceptions, some languages do not have exceptions. How would you deal with that? It's completely unmanageable. So Babelfish tries to unify all the languages and find the entities which are similar for each language, and exposes an API to access all of them at once, without having to write an SQL query for each type of language. And this is how it works. In Gitbase, you parse an AST, and then you run an XPath query. So XPath is a language to find information inside a graph-like structure. It's typically used for HTML or XML. Here we use it for an AST. So we ask for imports. We ask which, for example, Python packages we are using in all our Git repositories. Just this case in Go. Sorry, it doesn't really matter. We also have packages. We just extract all the imports and we can do something useful with them. This is just one example. You can extract pretty much any entity from an AST and do something with that. You can mine any way you want. The second tool, also from Sourced, is named Hercules, which is written in Go in terms of data processing, but all the data analysis is delegated to Python. It's also for analyzing a single repository. So Gitbase works best with several Git repositories. It's where it shows its full strength. Hercules works by design on a single Git repository, but it allows you to write any processing code in Go. Go is quite easy to learn, 2 days, and you already know it. It's not hard, it's not even like Python. And for God's sake, it's not like C++. It's much simpler, so it's quite accessible for everybody. Spend 2 days, and you're super proficient in the language. This is one of the reason Google designed it and developed it. So we can define anything you want, and you can reuse different analysis. You can build it directly to cyclic graph and do mining as adults do it. This is an example of applying Hercules. All the flows which I showed in my presentation, all these 3 examples were actually generated from Hercules. It's open source, so yes, a bunch of simple comments, and you reproduce the flows from my presentation. So speaking about datasets, why would you need a dataset? I mean, you have your personal source code, you can run a tool which was presented and get the result. Why do you bother? If you want to analyze many projects at scale, if you want to deal with big data, you are going to need a dataset. Imagine that you want to process all open source repositories written in Go on GitHub. If you want to clone all of them, you'll have some hard time, because cloning is hard. You'll be rate limited, GitHub doesn't like it, and also you have to deal with segregating several forks together. For example, you know that on GitHub you can fork a repository, so how would you deal with that? You need to go to the same repo. So you have to actually write a lot of source code. It's already written. And there are datasets existing and waiting for you. With a quirk, which is GDPR. If you heard about it, of course you did. GDPR has some limitations on how you deal with private information. And Git is actually in a kind of gray zone because every commit in Git contains personal information, contains your name, contains your email. It's not so good if you want to build a data set and expose all this information as is. This is why all the data sets which exist in the wild, they typically have your personal information removed. If you take the data set from Google, for example, they hash your emails and names. Any other data set, pretty much everybody does it. Just because if you don't, you will be sued. You expose the personal information. Why GitHub is not sued? Because there is like a very important note in the law that this personal information doesn't have to be the core part of the whole system. And in Git, if you change anything like your name or your email, your commit hash changes. Everything changes, and you get a completely different Git repository at once. And everything is screwed up. This is why it kind of works. This is why gray zone and not black zone. So the first data set is from Software Heritage. It's a French academic startup, a non-profit organization. They want to collect pretty much everything written in the world, aggregated. Maybe you heard about Web Archive. So it's the same as Web Archive, but for source code. They want to aggregate everything. And they publish a data set with just the graph. Everything, but no source code. Even without source code, it's a huge amount of data. If I'm not mistaken, several terabytes, probably 5 terabytes of graph data in various formats. You can just download it and play with it. It contains everything. Of course, impersonated because of the GDPR. The second data set is from sourced, which is the public Git archive. It's quite close to the concept of a code lake, so it contains original Git web files, original Git data, which you can use. Unimpersonated, of course, you can use it when it changes. Contains not so many repositories, but even with 260,000, you get 6 terabytes. It's a huge amount. You don't have to download everything. There is a tool which allows you to only fetch Python or Go, and also you can query for the number of stars. So it contains more than 50 stars. You can ask for all which are more than 100, for example, or 1,000. You want to memorize only the most well-known to the community. To summarize today's talk, here are the core insights which I want you to remember. If you have a similarity matrix, a matrix where every cell corresponds to how much a pair of items are similar to each other, apply swivel, apply TSNE, and you'll get these nice 3D visualizations, and investors will love you. And if you have a distance matrix, you can embed it with TSNE or with UMAP, and again show it in 2 dimensions, and again investors will love you if you have a startup. If you have time series, apply dynamic time warping as a distance measure, and again run this, and you'll get the results. Investors will love you. However, triangle inequality doesn't really make you elegant from the mathematical point of view. If you have sequences or heat maps, I'm pretty much sure many of you will deal with heat maps if you devote yourself to data science or to machine learning engineering. You can apply seriation and get the best, almost the best possible way of grouping elements in your matrix and in your heat map. And finally, I hope I convinced you that mining development history is fun. Did I? I hope so. So apply the tooling, use the data sets, and play with it. 3 more things until I finish. The first is the book, which is called Software Design X-Rays, written by Adam Thornhill. It's a brilliant book about mixing the concepts of psychology and software development to find insights. The author is not a machine learning engineer, so although he gets all the things, let's say, right, the book doesn't contain machine learning really, but you can use it as an inspiration if you want to do it yourself. The second thing is Mining Software Repositories Conference. It's an academic conference. It's quite prominent, probably the only biggest in the field. You can open the website and find the papers from the conference. It happens every year. Some of the papers are really nice. For example, there used to be a paper about Jupyter notebooks. The author tried to mine all the Jupyter notebooks in the world, which are open on GitHub, and reproduce them. How many of these notebooks would reproduce? The answer was quite low, unfortunately. The third and the last thing is Sourced Community Edition, which is accessible by this link. It contains all the open source tools Sourced has developed for mining software development history and also for engineering observability. It contains gateways and Bible fish and everything. And the good thing about that is that you don't have to set up anything yourself. You just download a binary, it's ready to go, no dependencies, you run it, you get everything, and you just point it to the directory with your git request and do the job. You don't have to mess up with Docker or compiling something or installing Python. You don't have to do anything like that. That's all I wanted to say today. Thank you very much. The presentation is available online and my contacts are on the left. Thank you very much.